Hey everyone, welcome to this explainer. Today, we're diving into something pretty wild. How abstract math actually acts as a real-world mission briefing to decode the physical space around us. You know, we so often look at math problems on a page as just numbers and symbols, right? A total chore to get through. But if you shift your perspective just a little bit, they transform into something entirely different. They become literal instructions for mapping our reality. Today, we're going to explore a seemingly simple sequence of exercises that reveals exactly how we can measure things we can't even physically reach.
So this brings us to a fundamental, centuries-old dilemma. How do you measure the unreachable? Really think about it. If you're standing at the base of a massive structure, maybe a modern skyscraper, an ancient monument, or a towering antenna, how do we calculate its exact height without dropping a giant, impossible tape measure from the very top? The physical world presents us with these massive, solid barriers to direct measurement. We desperately need a workaround. We need a way to translate what we can easily measure on the ground into the enormous heights stretching up into the sky.
And this is exactly what makes our source material for today so brilliant. Consider a standard, unassuming textbook page, labeled Exercise 1. It honestly just looks like a standard list of 4 word problems printed on paper. But I don't want you to look at this as just a math quiz. The text actually contains 4 distinct, escalating spatial puzzles. It's a carefully designed progression that trains us to see the invisible lines connecting us to the world above our heads. We're going to break this code apart, step by step.
Okay, let's kick things off with Level 1, Towers and Columns.
To crack these first 2 puzzles and map out rigid vertical structures like towers, we need a highly specific conceptual tool, the angle of elevation. Imagine you're looking straight out at the horizon. That flat line, that is your horizontal plane. Now imagine you have to tilt your head up to see the top of a tall building. The angle created right there between your straight-ahead line of sight and your tilted-up line of sight is the angle of elevation. The crucial point here is that this angle is our geometric superpower. It is the invisible hinge that connects our distance on the ground to the unreachable height in the sky. And it's the exact mechanism we'll use to solve problems 1, 2, and 4.
So let's put this superpower to the test with Puzzle 1. The text lays out a very clear scenario for us. We're standing precisely 90 meters away from the foot of a tower. That's a measurement anyone can take just by walking along flat ground, right? Then we look up at the top of the tower and our angle of elevation is exactly 30 degrees. The objective? Find the height of the tower. We have the flat ground distance, we have our upward angle, and our mission is to calculate the cowering vertical line. It's a classic, straightforward application of our spatial mapping tool.
But here is what makes this progression so brilliant. The text totally flips the script on us. In Puzzle 1, the angle was a known 30 degrees, and the height was the mystery. But looking at Puzzle 2, the text asks us to find the angle of elevation itself. And instead of giving us easy, concrete numbers, it throws algebraic variables at us. It tells us there's a vertical column that is 3h meters tall and a point on the ground that is root 3h meters away from the base. We actually have to use those 2 variables to work completely backwards and uncover the angle. It's the exact inverse of our first mission, forcing us to understand the geometry from a completely different direction.
Moving right along, we hit Level 2, the slanted line.
We're shifting gears entirely here. We're moving away from static, concrete towers anchored to the earth and looking at a dynamic physical challenge up in the sky. Walking through the exact variables of this third puzzle directly from the text. Step 1, we have a kite flying directly above the ground at a height of 60 meters. Step 2, the string attached to that kite is temporarily tied down to a single point on the earth. Step 3, the inclination or the angle the string makes with the ground is 60 degrees. And finally, Step 4, the critical physical constraint, we must assume there is perfectly 0 slack in the string. It is pulled taut, creating a flawless, straight, slanted line cutting right through the air. And this leads us to the exact question posed by the text. Find the length of the string. You can kind of feel the stakes of this puzzle, right? We aren't just measuring a flat distance on the ground anymore. And we already know the vertical height is 60 meters. This time, our mission is to measure the physical connector itself, that taut, slackless, slanted line slicing upward at a 60-degree angle. By assuming there's 0 slack, the physical string becomes a perfect geometric hypotenuse, locking our vertical height and our ground angle into an incredibly solvable real-world puzzle. All right, take a breath because we are entering Level 3, compound elevation. This is essentially the boss level of our explainer. We're now dealing with an environment that features multiple interacting structures. Let's carefully list out the moving parts of this final puzzle so we don't get lost. First, we have a building with a known height of 15 meters. Second, if you stand at the foot of an adjacent tower and look up at the top of that 15-meter building, your angle of elevation is 30 degrees. Third, if you walk over to the foot of the building and look all the way up to the top of the tower, your angle is a much steeper 60 degrees. The ultimate objective? Figure out the height of this unknown tower. Listen to the exact quote from the text. The angle of elevation of the top of a building from the foot of a tower is 30 degrees, and the angle of elevation of the top of the tower from the foot of the building is 60 degrees. I mean, wow. Just hearing it, you can practically visualize those interlocking sightlines, can't you? It's an intricate physical puzzle. You have to mentally place yourself at the base of one structure, trace a line of sight up to the other, and then cross back over and do the exact reverse. The heights and distances of these two completely separate structures are intimately linked by these crossing, invisible lines of sight. It literally tests everything we've learned in the previous levels.
So, what does this all mean? Let's look at the overarching takeaway.
Think about the journey we just took. We've gone from measuring a single static tower to finding an unknown angle to finally mapping two opposing complex structures. 4 questions, 4 little paragraphs of text. But, as we've seen, it represents a remarkable progression. It proves that with just a few basic, grounded observations, knowing exactly how far you've walked or simply the angle at which you tilt your head, you can map totally unreachable heights. A simple line of sight unlocks the physical secrets of our spaces. The abstract math in these exercises is actually an incredibly practical toolkit for understanding scale, distance, and dimension in our 3D reality.
Which leaves us with this final thought to ponder. When you walk outside today and look at the skyline, the trees, or even a kid flying a kite in the park, what do you see? Are they just isolated objects? Or after going through these puzzles, is the physical world around us actually just a massive series of hidden triangles waiting to be decoded? Keep looking up, keep looking for those unseen angles, and suddenly the unreachable doesn't seem quite so far away after all. Thanks for joining me on this explainer.